show something that just said they're going live. He's going live with mics. So mics are live now.
Okay. Well, I'll just leave that up. as
Yeah.
a
So
Background and then
you're going to speak from
Perfect.
here, Mark?
I don't know. Mike, can you turn your
Stay
camera
right here.
on?
It did. I just turned it off until we were, I mean, I think they said we're live on Facebook now and the mics are on, but
Mine is great out, but they can pick me up
yeah.
with that camera, right?
Yeah.
They're picking up
Yeah.
the room. So. Last year, comes back in.
Lucky you.
Whatever.
How's that working, Mark?
I think it's already on.
Yeah, we don't touch it.
I don't have to touch it.
You ladies.
So mics are live. We
I have
can hear you
questions.
through these mics.
Okay. Do
You're
I?
still sharing screen, so you actually
Yeah.
want to stop that until Mark's done with his introduction.
Okay. Do I need to turn on my video at some point? Because it's grayed out.
Oh.
I
That's
don't know
not
why.
good. Thank you for, is yours grayed out too?
No, I just stopped it until we got going. See, mine works.
Maybe.
Catherine's lucky.
Let me take a look.
Which one of you guys are going to start?
I'm gonna start.
Okay.
So the green means all these mics are live. So for those of you who are on the webinar, stay tuned. We'll be starting shortly. Working out last minute IT details, but we will be starting in another minute or two. For those of you just joining the call, this webinar, stay tuned. We'll be starting in just a few minutes, just a minute or two.
No?
Well, Gerald was trying to fix something with my video. I don't know if he's going to.
Your video seems to be working.
Yeah.
Yeah.
And your video is not.
It's not.
You disappeared on me. Okay. So
Yeah. She disappeared on me. Like I don't have her anymore either.
Really?
yeah, completely. Like you're gone from,
I'm up
The
here as
meeting-
a participant panel.
yeah, nobody else sees you, including.
No, it's
Can you
the
close
video
out
doesn't
and-
work.
Like exit out,
Like,
leave
Yeah,
out.
exit
the
out.
video is great. I
Well,
can't
you-
show myself.
Webinar.
Yeah.
I'm like, I'm
Yeah,
on.
that's, it won't be the end of the world.
I,
We'll just-
I was gonna say you can still see me on that camera.
Yeah,
So
I have no idea. other than
Okay.
Maybe you have an old version.
Yeah, just show the slide, speak to the slide.
well, I had to join through the browser because we're not allowed
Oh,
to.
that's exactly what
install-
it is.
Yeah.
Well, mine is too
But
though.
hers does, but
Oh.
her computer's newer, so
Yeah.
I don't know if that's the case.
Oh, Zoom, yeah, our government stuff does.
Yeah. Oh, God forbid you try to do anything new with a government computer.
What actually listed is blocked first.
But we have,
Hit launch
we have
meeting.
WebEx accounts.
Let me know if you.
So for those of you just joining the call, we will be getting started here in a moment or two.
Floodplain management study. Service.
I'm gonna try to elevate you again here.
Okay.
I'll give you guys the audio cue here. We are live and ready to go.
All right, welcome, everybody. This is a webinar covering the U.S. Army Corps of Engineers presentation on their project to develop a hydrologic and hydraulic model for the Antrim County chain of lakes. I'd like to introduce Mark Stone, who's going to speak and give a little bit of background before we turn it over to the Army Corps presenters.
Okay.
Mark, take it away.
Thank you, David. This project started, I believe, in excess of 3 years ago now. And it was born sort of under a lucky star because we found out through the grapevine that there was a program called the Floodplain Management Services at the U.S. Army Corps of Engineers, and that they made available some help for us to understand how our watershed operates more carefully. And so we applied for this program. And long story short, we ended up with a very generous grant from the U.S. Army Corps. It was in excess of $300,000 of work. And the county allocated, I believe, about $75,000 to match and contribute to the project. But the project is to build a computer model of the chain of lakes in order for us to have some predictive ability about how the lakes would behave, especially in the event of a large rainstorm or precipitation event. It's obvious really for us in today's world why something like this is important, but I can say that on a personal note, in the 25 years that I've been taking all of the complaint calls from people living on these lakes, sometimes I had a really good answer for them. And sometimes I didn't, because the bottom line was there's a lot of things that we really don't understand very, very well about how these lakes behave. And the only way that you can do that is to measure them and make calculations and actually figure it out. And it's a big job because it's a big chain of lakes. And so thankfully now it's really a great thing after this much work and many years of discussion to actually having a tool that is going to really change the game for us going forward on how we manage these chain of lakes, and especially with the concerns about things happening to our climate and the apparent growing frequency of these large storms. So I'd like to introduce the Army Corps team with which we've been working for these years. On my right is Shelley Thule, who is a hydrologist for the Army Corps, and Catherine Laboon, also a hydrologist. The two of them worked on the two components, as you're going to learn. And we actually have the people that made the model with us in order to explain it to us. And then on my left is Garrett Ray, who is the project manager for the project with Army Corps. So we're going to start with a presentation, and then we're going to go to questions that are from the small group of people that are in the room with us. And then we're going to open it up to the questions that are coming over the Zoom webinar. So would you like to start, Catherine?
Okay, well, I'm going to get our presentation up and give it a try. Okay, hi everyone. Again, I'm Catherine Laboon with the Corps of Engineers. I'm a professional engineer. I've been working on these types of studies for 20 plus years, 8 years with the Corps, and then previously with private industry. So I've seen a lot of different models, built a lot of different models, reviewed models. So well versed in a lot of the ins and outs of all the modeling. So Mark just gave a little bit of overview of why we're here. I'm going to talk about the hydrology part of this whole analysis. My colleague Shelley is going to talk about the hydraulics modeling, and then we're going to give a little bit of a demonstration of the hydraulics model and, you know, the results that we get and what you can do with this model. So first of all, we examined the hydrology of the system with using a model called HEC-HMS. This is a modeling software actually constructed by the Corps. It is free to the general public. You can download it on your computer, run it yourself. It is a way to represent basically the water cycle of the system. So if you remember back to like, 5th grade science or so, where you look at, rain falls, what happens to it after the rain falls, where does it go? Does it get caught by trees? Does it end up running off the land? Does it infiltrate down to the groundwater? HMS's goal is to simulate all these different activities as much as possible to figure out how you go from rain falling down to how much water do you actually see in the stream. So to build an HMS model, and this is the one that was just a picture of the one we built of the subbasin, you basically have to look at your watershed and say, okay, how can we represent the watershed? It's a bit of an idealized representation of what the watershed is, the lakes, the rivers, the different land uses, the different soils, all that goes into, looking at the basin itself, the whole watershed. And then you also need to look at, your rainfall. Are you just going to look at, rainfall, which is what we looked at for this project. We did not go into snow melt, but you can also model snow. That's an option. And then you also include what we call control specifications. So that just tells the model, we're going to look at the period from April 1st to April 15th and run the model for that time period and see what happens. So those are the 3 main components of the model itself. And so how do you actually start out creating this model? Well, you need to assemble all of your topographic information. You need to know, what is your watershed? There's a lot of published watershed boundaries done by other groups like the USGS and NOAA, but we can do this in HMS by taking the publicly available topography, which is what we did. We downloaded USGS topography. We ran the delineation to figure out the extents of the watershed. And then we subdivided the basin to calculate some inputs. And so we came up with, a representation of the chain of lakes watershed. And this is actually something that can be done automatically with the software tools now that we have in HMS. So that's a very helpful tool to use. So here's an example of, the topographic information that we delineated the watershed, subdivided it. And so this is the model that we get at the end. So once we have that basin divided, we have to start looking at, for each of the little smaller sub-basins, things that are going to impact how much water is going to flow off that sub-basin. So you look at, is there a lot of trees? Is the tree canopy going to capture water and not allow it to actually reach the stream? So are there crop fields that are row crops where there's a depression between the row crops where the depression can capture water, and so that actually just gets held there? How much water is going to infiltrate down? What type of soil do you have? Do you have clay? Do you have sand? Do you have gravel? How is the water going to infiltrate? And then once you know how much water is just going to not, once the infiltration rate is you reach as much as going to infiltrate, how is the water just going to flow overland to the stream? And then also how much water is going to end up in the groundwater table. That's all part. Now the 2 biggest or the 3 biggest components are probably your infiltration and how water flows and your groundwater. So those are the ones that we typically look at the most. So once you have all of your subbasins defined in terms of, your infiltration, how fast the water is going to flow, what's going to go to groundwater, you also need to include your streams. So for example, on the left-hand side, that's an example of the Rapid River and how you basically take the water from each subbasin and move it down the river until it outlets down at Torch Lake there. So reach routing, takes all the water and moves it down the stream. On the other hand, you have lakes, which of course store water, and they will store the water coming in and then they'll release it depending on what the outlet of the lake looks like. Is it an uncontrolled outlet? Does the water just flow out? Is there a control structure? Is there a dam or anything? So that all gets incorporated into the hydrologic model. So the next, that's get your basin, your watershed all set up, all the different pieces. So now you have to start looking at your rainfall. And there's at least a couple of different ways to look at rainfall. So we looked at both ways. If you just looked at rainfall gauges, and you can see on the left-hand side, these were all the different gauges and all the different sources of rainfall that we investigated. We used definitely the rainfall collected by the community. We investigated some rainfall by university, Michigan State, and then also airports are also always usually a relatively good source of information, depending on the airport and the time frame. But that's not all. You can also look at radar information. There's a lot of sources of gridded radar information where, they have estimated the amount of rainfall falling just due to the radar and that information. So this is, I don't remember, it's from June 2020, June 2020. So that's an example of, radar that was also used to look at the response of the watershed and how the water went from, rainfall to flow at the streams. So once you have all that information, you've got your basin defined, you've got your rainfall decided and what you're going to run, then you basically run the model with that information. And there's a couple of different pieces of information that you're going to get out of the model. So the top screen shows basically this is for the very upstream watershed of the Intermediate River, what the flow looks like over time. So the red bars at the top are the rainfall, and then the blue line at the bottom is basically how the flow comes up and down based on how much rainfall you have. And so another example on the bottom here, so the top is rainfall and then flow, and the bottom is outflow from the Bel Air Dam impoundment. So you can see there, I've got a modeled information, and then the black line is actually the data that was collected by the community. So you can compare the model results to the data that was collected. And actually that is the goal of what we do next, which is calibration. So the next step in the model is to adjust the model parameters to match the field measured results. So for example, this figure here, this is 6 Mile Lake, this is the black line is the observed elevations, and then the orange is how the model resulted in elevations. And so, what do we adjust when we calibrate? Well, we can make changes to like how fast water infiltrates, how much water infiltrates, how fast water flows overland, how fast it flows in a channel, and then how the lakes store and release water. All of these things, are not defined necessarily going in. These are things that you have to define and adjust slightly to make your model match the observed data. And that's the whole goal of calibration. So just a quick summary for the hydrologic modeling. HEC-HMS takes rainfall, simulates the water cycle, and it estimates the volume of flow per time. So you get a volume out of the model, and you go a volume per time, and you can do it at different points in your watershed. You can just look at the very outlet. You can look at different locations, and that's what we did. We got the results from a number of different locations that are then fed into the hydraulic model that Shelley's going to talk about next. But the thing that we get the most out of this is, so for example, on the very right hand side, you see the hydrograph, and you see a peak flow at the top, and then you see an actual volume and the timing of the flow. So both of those pieces of information are typically used. Peak flow is used if you just want to see what happens if you have a peak flow everywhere in your watershed, but then you also run the whole entire hydrograph so you can see the water come up and go down. So that's what we get out of the hydrologic model, and that's HEC-HMS, and that's the part that I did. So I am going to hand it off to Shelley.
Sorry, let me get this
to
to the right
talk about
spot.
the hydraulic modeling.
Let me present. Slideshow. All right. So while Catherine talked about the hydrologic cycle and the modeling that was done to get the estimates of how much water will actually get into the river and the timing of that, the hydraulic modeling, we use the Hydraulic Engineering Center river analysis system. And what we use that for is to figure, okay, now that we know the amount of the volume of water into the river, how does that water move downstream? As you hit man-made structures or just even natural, widening and narrowing of the river, water levels will be modified based on those structures or those things. So our hydraulic model will take care of that. So on the left, or basically we put in here that HECRAS is used for really anytime you want to look at the water levels in a river system. So FEMA will use it for their floodplain studies. USACE, we use it a lot for stream restoration studies. Sometimes they'll do ecosystem restoration projects, things like that. Sometimes there'll be analysis on, banks that are failing, and we'll have to do analysis to stabilize that. So you can really use the model in various ways. On the left-hand side is kind of a typical floodplain that we look at it. If you took a river and cut a line straight through it, that's kind of this cross-sectional view, we call it. And you can see where there's darker blue on the bottom, we'd call that like our normal base flow event. Usually it's the water that's normally in the channel right here. I think you can see my mouse. And then as you get a flood event that, rainfalls coming onto the surface of the land, running off, and it gets into the river system, you start to get, water accumulating in the river system. And as that happens, you'll get your water surfaces increase. You start to see a larger floodplain, water levels will increase, and usually you have to go out wider into the floodplain. So there's usually different banks along the river. There's a natural lower bank, and then the full floodplain, and then like really large, valleys, if you will. So that's just kind of example of what we look at with the hydraulic model. This is just an example. It wasn't in this watershed, but Antrim County Emergency Management in Gaylord had you have flooding in the area up here. Every recent rains being localized flooding, and you can see there's overtopping of water on this road. This type of model will let us look at, do bridges and roads overtop? If so, by how much would we expect? Things like that. And I don't like this photo though, because you should never drive on wet roads where you don't know how deep it is. That's very dangerous. Don't do that. So when we build our model, there's multiple components. The first thing we have to do is look at the geometry. So we're trying to represent the system as best we can. And so that's usually where I'll get into this a little bit further. It's the geometry of the terrain, the land use, what's your bridges, what are the dimensions of your bridges? Is it a culvert with a small, size, CMP, corrugated metal pipe, or is it a regular bridge with a nice span? All of those inputs we put into the geometry file. And then we need to know how much water is in that system. So we call that our flow file. That is really what I create using the output from the HMS model. So the model that Catherine created, all of her hard work gave us some hydrographs. She kind of showed those rising and falling flood waves, kind of, if you think of it that way, as water level or the discharge increased over time. I take that and put it into my model as an input. That's where we kind of start the hydraulics here then. And then we create a plan file, which just says, what geometry file do you want to match which flow file? Because once we create a existing conditions geometry, the program becomes a nice tool where you can make a copy of that geometry file and change things. What happens if we have to replace a bridge? Well, do you replace it in kind, or do you make a change to the bridge? If you make a change to the bridge, you can model what that would look like and how that might impact the system. So it becomes a nice tool to be able to run those type of scenarios. So creating the geometry file, that terrain file, we download data, LiDAR data, terrain data. So basically we want to know what is the elevation of the ground everywhere where we think will possibly get wet. So the main channel and then the overbank floodplain. So luckily the USGS has a repository of terrain data that you can usually download data from. At this point in time, the state of Michigan has flown Antrim County with LiDAR data. Basically, they fly a plane and they send signals down. And as soon as it hits ground and it bounces the signal back up, they call that first return. And they do some processing of it and they can get to what they call bare earth. So like if it hits a tree leaf, that returns up, but then there'll be a lot of signals that hit the ground too. So they filter out all of the fuzzy parts, if you will, the tree leaves and stuff, and then just get the elevation of the ground. Pretty much everywhere in the county has these 2-foot grid cells, which are nice and helpful for our modeling. But because that hits the water surface and returns, we don't know what's happening in the river. And that's the main part that we're concerned about. So we have to send out surveyors to get channel geometry for us. So they'll go by whatever means they need, whether it's a boat, remote control boat nowadays, sometimes they have, or if they have to wade the river and grab the data manually, we get those data points. So this is an example of the terrain data I was able to download, and someone actually, was able to get all of the channel data for me. So we kind of had these spaced every few hundred feet. I think on average throughout the system is like every 300 feet, we had a cross section of survey data taken. And using that, we can interpolate a nice channel through the river. So this is a very example of, if I cut a cross section, it was very short here. From here to here, you have the overbank terrain, and then you can see with the LiDAR data, it was flat. This was the survey data then that was collected. And then we can create one seamless terrain that has the ground elevations with the channel nicely kind of cut in and modeled. And that becomes the base of our hydraulic model. That's, the base river, if you didn't have any man-made structures on it, and you just cut your cross sections along the system, that would represent it. But then we get to add in other features. So we'll develop our cross sections. So we use that terrain, we'll cut our cross sections, and then we can add in our structures, our bridges, whatever, information that we need to add in. So this says bridges and culverts. Those are, I think, are most people understand what they are. I will say culvert, sometimes you don't that's not a term that a lot of people understand. I didn't hear of it even through school. I remember getting to my first co-op position as a student, and someone said culvert and I didn't know what it was, and I felt really silly. But you shouldn't, because most people don't know what that is. So basically, if there's like a pipe, usually, whether it's concrete or corrugated metal, they're usually the smaller bridge crossings, whether it's driveways or just smaller roads. And you look down and you see a lot of the whether it's the concrete of the bridge and then a small opening that we just call a culvert. Whereas bridges usually have open spans and water flows underneath it a little bit better. Inline structures are basically dams. It's just a term we use in hydraulic modeling because it's a structure that's in line that controls the water levels. We're not necessarily creative people. And then levees you can put into the system if you have any to represent how that might control the water and keep it contained within the channel. So in this case with the chain of lakes, it was very important to incorporate your lakes. They're such an important part of the system. So we had some maps from the 1940s and 50s. The state of Michigan went out and pretty much surveyed all the inland lakes in Michigan, or at least a lot of the large ones, and created contours, depth grids of all of them. So we took those maps, we kind of linked it up with an elevation at the shoreline, and we were able to digitize them and get them into a digital terrain format. And then we were able to merge that directly into our terrain data also. So that was a lot of, we call it GIS, Geographic Information System, the manipulating of that type of terrain data. And we were able to add that in. And that's important because when we were modeling the system, we modeled the rivers that connect the lakes as rivers and reaches, but the lakes themselves, we modeled as storage areas. And so those storage areas, basically, we just use a curve and we call it a elevation storage curve. And we use the terrain data set and it will calculate a curve. You can kind of see one here It says at a certain elevation, what's the volume of water that can be held in that lake? So once you kind of can define a lake by the storage curve, as water comes in, the inflow, and it runs its calculations on what the elevation is, it'll know how much water can be stored there, and that will impact how much water can flow out. So you'll have a river system flowing into the storage area, the lake, that will rise and fall based on the storage curve. It's how much water the lake can hold, and then move downstream. So this took a while of GIS manipulation, but it was an important part of the hydraulic model to really kind of figure out how those lakes work in the system. So once you have all of your geometry kind of set, right? You cut your cross sections, you put in your bridges or your dams, you got your storage areas, our lakes set. We have to add in our flow files. That's like the next component. And this is where we get the output from Catherine's model, that hydrologic model. And so again, what the hydrograph represents is the amount of water. It's like the volume, the discharge. This says meters per second. Our model is in feet per second. But how much water is coming through the system over time. So as you might start your hydrograph lower, smaller discharge. As rain comes down into the system, moves over land, gets in the river, that's all Catherine's model. It starts to accumulate in the rivers, and you get a rise of your water levels, and then it'll hit a peak, and then it will, recede, the receding floodwaters. So a steady state model just looks at the peak flow, and that's it. It's a single step in time. It's what would the model look like if you only modeled the largest discharge, and that's it. So you get a snapshot in time. So a lot of, let's say, FEMA models in the past would use that steady state, but that doesn't tell really the true story of the system. You don't know, as the flood wave moves downstream, how the water levels might rise and fall at one lake versus another as the water moves downstream. So an unsteady state uses the hydrographs, because then it puts that time component. If water's coming into a system all at the same time throughout, then you might have the lower peak move down as the upper peak comes in, or are they all accumulating in the river at the same time? So the timing of the peak flows really kind of makes a difference. So the unsteady hydraulic model that we're doing kind of does that. This one just showed that we had like 30 inflows coming into this. So Catherine showed all those small basins coming in. We would take, and we had to figure out where those inflows would meet up with my hydraulic model and put in all those individual inflows. So this was over the course of April through June of 2020, because we had some good lake elevation data so we could calibrate the models. So each of these were probably like a different rain event that happened in those times. You can see how some basins might have a lot more discharge than others. That could be just due to the steepness of the slopes, the land use, all the stuff that Catherine's model kind of figured out for us. So then we run our model, and at every cross section or every like storage area, whatever, we'll get a water surface elevation over time. So when we get that, if you didn't have calibration data, all the assumptions we made, just as Catherine said, there's things in her model that you can adjust for inflows and things like that, to how much water gets absorbed versus runs off. In our hydraulic model, we also have features that can be adjusted, and there's a normal range that you would expect, but within that range, there's some play within like the physics. So how fast water moves down your stream channel based on your stream bed or vegetation. We call those our N values. I think of them as a friction factor, because most people can understand that, right? You have something that's super smooth, and if water went over it, it could flow faster down. If you have something that's rougher, it will be slower and held back more. So if you think of that as like a nice river that has few weeds and very straight and it's nice sandy bottom, water will flow through it pretty fast. But if you have an area that has a lot of grass and there's a lot of meanders, and maybe even in the banks there's shrubs that like in vegetation that start to grow in the channel, we put that as we call it N value, but it's really a friction factor. And so we increase that a bit. And so as is, every location in your stream system, you have to make assumptions of what those are. and you go out in the field, you look at photos, you look at the vegetation, and there's reference manuals. There's a lot of very smart people that have done years and years of research, and actually the biggest one that we use, Joe, is like 50 years old, I think, and it's considered the thing. But you just look at the reference tables, but you can modify those things. And so as we run our model and then we have observed data, you can change those a little bit to see how the peak flow of our model might match the observed flow, and if the timing is pretty decent. It's because you want to try and calibrate your system to that real data. Once you have that, it gives you better results. So once you can calibrate your model to any known observed data, in this case, this was all within, I think on this particular lake, plus or minus like a quarter of a foot. This one came out really well. I was happy. All of them came within pretty much a half a foot, and for 12 lakes in the system, like that's considered very well calibrated. I think there's one lake that was a little bit higher, but like this is the goal, is to calibrate the model to have a running existing conditions model that you feel represents the system well. What?
It's not showing the right thing.
Oh, sorry. Let's see. This is not showing my current slide. Probably. Let's see. Has something happened to that one? Because this is still showing on the internet.
Sorry, folks, technical difficulty there.
We're just getting to the good stuff. It's all been good. I don't know what's going on, but this isn't showing what's going on up there. Should I exit out of this? Minimize this. Go to the internet one. Is it sharing now? Look, Catherine, do you want to share and you can put up that screen?
Yeah, let's try that.
Yeah. When we get to the model, we might still have to play with this, but we can at least finish this part. Showing it? Or do I have to officially stop sharing? No, I'm not sharing.
There we go.
There we go. That's the calibration one. And they had asked up on the internal viewing, do you have to see the side? All right. So this was the calibration of the results, where we can see the black line is the observed data that was collected over those 3 months. And then the model run in blue. So when it's showing that, you know, it's following the rise in water surface elevations, it's coming back down, and it's matching quite well with those observed data. Next one. So post calibration, once you have a model that's calibrated, and you feel like you have a good existing conditions-based model, then you can understand how your system might work as a whole for what's currently in place, but then it can be used for other purposes. So mapping floodplain extents, FEMA standard annual exceedance probability storms. So you've probably heard of FEMA floodplain maps and risk assessments. And basically that it's a way to provide information on what's your risk of flooding as a tool, just because a lot of people don't understand their risk. And so once you have a hydraulic model built, those type of things can be determined. In fact, FEMA is currently doing a study in the area, and because we spend a lot of money on the survey data and we've created this model, they don't have to do it now. So we can give them the model, and they're going to take our model and use it for their study. I don't know if they'll make any changes. I don't know if they'll do the steady state versus the unsteady, because they really just care about that peak flood. But they'll have the base model to do that study on. But then you can also do things that I think are more fun. Looking at proposed conditions, what happens if you want to replace a bridge? What happens if you want to do some kind of dredging in a certain channel? And how would that possibly impact the system? So you can do it as a way to learn how the system responds to a change. But also if you have a specific project in mind, let's say you want to change a bridge, you can do optimization runs. So you can say, okay, what happens if you have a size this opening? How does that impact water levels? And sometimes you want to compare that to the costs of that opening, because sometimes maximizing out the bridge size opening helps water levels or not. But if the cost is prohibitive because it costs too much money for that size span, there might be, you know, some kind of optimization in there. So you can start trying to run the model for those types. So go to the next one. So the summary with the hydraulic modeling here is that you create this series of cross sections that represent the river and the floodplain to represent that, you know, existing conditions. Then you can run those flows through it, and then you can show the results, which is water levels and the floodplain maps. And just, you know, depth grids too. You can look at velocities in the channel. There's a lot of information you can get from those, which is really kind of nice. And another thing is when it's an unsteady res model, the timing of the flood wave too, so you can understand how fast things might be moving downstream in a relatively, you know, I don't want to say flat, but like, you know, state of Michigan where the glaciers have wiped us out. I'm in Southeast Michigan and we're pretty flat. Here there's some topography, but it's relatively flat. So the timing isn't as much of an issue, but if you're in areas that are very steep slopes, very fast floodways can come through, and knowing that a peak flood wave can come through in hours, that can, you know, that's important to know that timing. So that we didn't have on here, but the timing is, I think, an important aspect also. So basically, this is just the information for me and Catherine. It's our emails and our work phone numbers. If you have any questions, you can always contact us. So we can also demo the model, but should we check for questions first? Let's see. Do we have questions? What?
Why don't you go ahead and address the three questions that
Oh, okay. Yep.
we purposed for you.
Okay.
Yeah, so as you're bringing that up,
Let's try.
people online, who, if you have questions, you can type them into your Q&A item on Zoom, and we will answer them at the end of this presentation. So if you have questions and you're on the Zoom webinar, type in your questions and we'll get to them. We'll be answering questions from the floor here live first, and then we'll get to the questions that the people on Zoom who are listening in can ask. Go ahead.
I'm trying. It says it has started sharing the screen. I see it on my screen. Oh, let's try it again. Anything? Nope.
Have you unshared?
Shelley, you might need to disconnect and reconnect.
Okay. Let me log out and then come back in.
While we're doing that, are there any questions from the floor while we're going through this relogging in process?
Mm-hmm. So the Corps of Engineers, we have a lab called the Hydrologic Engineering Center. So the website is hec.usace.army.mil. And so there are hydrologic experts and hydraulic experts, and they've pretty much created the models. They write the programs for it. And so through that website, you can download the programs. There's training material up there. Actually, you can download. There's even links to YouTube videos now that they have for like learning how to use the system. So it's pretty impressive.
Now, the model files for the Antrim chain of lakes are pretty huge. It's about, I'd say, I think it's about 120 gigabytes of data. And what we'll be doing is we'll have hard drives available here, probably in Pete Garwood's office, in the coordinator's office. And people will be able to come in and bring their laptop in and then download those data files directly on their machine. If they want, you know, the all the full complement of files that were worked on Antrim. So the software that Shelley's talking about is the software you need to install on your laptop in order to run those data files. But anybody that wants to take a shot at using HECRAS or HECHMS on the Antrim chain, it's public domain files and they'll be available here. Well, yeah, before we did the public meeting this afternoon, we held a technical handoff meeting at which we invited engineers and people in the industry to meet with Shelley and Catherine and kind of get the scoop on how the software was set up, et cetera. And so there's always already some awareness, but as people become aware that this is even available, we expect more and more folks are going to be interested. We will also have, there's written reports. There's a written report on the hydraulic that Shelley worked on, and also a written report on the hydrology model, which Catherine worked on. And those will have available on the Antrim County website, and people will be able to download those as PDF files. Those are essentially, those reports essentially document how they put the model together and explain all the data resources and so on, and their logic that goes into the creation of the model. And then one other thing I would just like to point out, in case it doesn't come up, is that when someone is actually utilizing this model, they've got it installed on their computer and they're working on it. Catherine and Shelley put a great deal of effort into actually inserting documentation into the software files themselves. So when someone's looking at what logic there was and how they put in the parameters for the culverts at Ellsworth, right there in there, they'll be able to bring up comments where they have explained why they put that information in there, where they got the information, how it was surveyed, who surveyed it. And this is all important because this model is going to get used for a lot of very important work going forward on the chain of lakes. And so for it to have high scientific credentials, you have to have the information. You've got to have this background information so people are not just taking an assumption that, oh yeah, this is all good stuff. It's documented in there. If you don't believe it, go back, check the original sources. It'll all be available in there.
Okay, thank you, Mark.
Yeah.
Are we back?
We're back.
We're back.
Great.
I had to log off to log back on, I guess.
All right, so
Like,
let's keep going.
It kicked me off. So real quick, because there's questions on the website for the HEC, it's just hec.usace.army.mil. Honestly, if you just Google HEC Army Corps of Engineers, you'll find it too. So this is what you get when you get there. On top here, there's software. This is all different software that they've created that's free to download. But we're talking mostly about HMS and then HECRAS. So for example, if I go to HECRAS, it'll take me to the main page for HECRAS. It'll go to the downloads and you can then download the program right away. And then there's documentation, there's known issues. There's what's nice with the documentation is it will give you searchable files that you can look at for the user's manual, how to input the data, reference manual. When I said there's things that you can look up for, let's say those roughness factors for the stream, there's tables in that reference manual. So if you go to the documentation page, all of those are there. And then there's the HECRAS training, and any training material that they have that's available, you can download it or view it. So the HEC website is really nice for that. So, okay, then going to the hydraulic model, when you first open HECRAS, this is what you see. It doesn't look like much. It's just this box that's sitting here. But this is what links all the different parts that I talked about together. So when you first start the model, I mentioned the geometry file. So this is my geometry file. And then we have the blue blobs are my storage areas. I just did them large to create those storage area curves because why not? And then there's the rivers that connect. And so when I zoom in between each of the lakes, you can see the cross sections. We're moving a little slow, but we're going. So there's these green lines are cross sections, and each of, oh, it's catching up on me. And we can look at farm fields too. It's still going. Sorry about that. I got a little click happy, I guess. Anyways, cross sections. Each of the cross sections are represented, all of those lines through, we have a representative cross section. So a nice way to look at this is actually in Raz Mapper. And I can open that up. And like here's an area near Bel Air. And all of these green lines are the cross sections that we used. So you can kind of see the train. Let me take off the aerial photo for a second, just because I think that makes it clearer. While this looks very colorful and bright, that's what we call our train data. And there's a guide here for what the elevation is at any point. What's nice on that is, if you know, it's very detailed, and if I hover the mouse anywhere, I can see what the ground elevation is at any given spot. So we even merged in channel data, so it's all combined. For an example, I just use my measure tool here, and I can just kind of cut across if I wanted to show you plot train. It gives me what the ground elevation, so that the river is here because this is that wide flat area. But we would do that for all of the cross sections that we want to represent our floodplain. And so what's nice there is that once you have all of these cross sections put in, we have the Bel Air Dam modeled, we have bridges modeled, you can start to run those scenarios. So I think one of the things like they want to show is what happens if we get a large flood event, something like 5 inches of rain over the entire basin at once. What would that look like? And that's where you would start to get, you can look at a depth grid here, and you can start to see what that flood wave would look like. So if you had 5 inches of rain over the entire system for, over the course of 24 hours, you would see that you would start to get that flood wave that moves in and floods in those like marshy areas. This is near Bel Air, Lake Bel Air, that near downstream of this is where Grassy River comes in. You can just see, that marshland that like slowly floods in and then floods out. And so that was the flood wave that was modeled. So if you look at where we started, the minimum, at the start of the study, and then you look at what that maximum floodplains would be, you can start to get an idea of what would happen to the system with that 5 inches of rain. So you could do that for like 1 inch of rain. We had the Corps of Engineers did a study once in Tennessee, where they want to know when the National Weather Service says you're going to get 4 inches of rain, or you're going to get 5 inches of rain or 10 inches of rain, what does that mean in your system, right? Like that doesn't tell you too much. You might think, oh, that doesn't sound like a lot because it's just a few inches, but how that water accumulates, Catherine's model, and then what does that mean in our river system? So we've done studies in the past where you can model in the hydrologic model, what happens if you get 1 inch of rain, 2 inches of rain, 3 inches of rain, and then you just model all of those different scenarios in HEC-RAS, and then you start to get an idea. So they've used that to talk to the public and release information on the risk of, what happens if the National Weather Service says a certain amount. So again, those are all things that can be done once you have a model like this built to represent those systems.
While you got it up, why don't you zoom in on the Bel Air Dam there and show the 1% storm progression?
Okay.
And this was based on 5.1 inches of rain over an 8-hour period, correct?
12 hours.
12 hours.
24 hours, sorry.
24-hour period.
Yeah.
Okay.
So
It's almost totally blocked for vegetation in the river.
well, there's vegetation that's in there, but it's not totally blocked. It's
Yeah.
water flows.
A reminder here, folks, nobody can hear the questions being asked
Oh,
online.
Hold the questions until,
Yeah.
okay, so just to make sure everybody's clear what we're looking at, this is the Bel Air Dam. You can see the river here. The red lines are the regular banks of the river before the rain event.
Okay.
yep.
Okay, so this is at normal operation. You can see the dam, you can see the river is inside the banks.
Aerial
You can
photo.
see the topography.
Aerial photo. There.
Here's the
You
aerial.
can see,
photo there,
yeah,
too.
there's Bel Air superimposed on top of it.
So you can see the North Bridge Street, you can see where the dam is, you can see where Riccardi Park is.
And
Anyways,
then run the simulation. So you can see the water start to flood and then hold it at the peak.
we'll let it recede back and then I'll go to the max. So that was how the flood waters kind of come in and then recede. Then we can look at just the max extent.
So this is the max at the height of that peak flood event. You know, looking at this. So this is an example of what this model can do, the power that this model can give us in looking at various scenarios.
And then, so this is obviously looking at the extent of the flooding, but if I'm on my depth grid here, I can hover over it and you can actually see what the depth of water would be too. So obviously in the poundment, you're at like 5 feet, 7 foot, you know, depending on where you're at, 12 foot, 13. But like in the park area here where it floods with that large flood event, you can start to see how much the depth of water would be expected in that park area, like anywhere from at the end 0 and a foot and a half, 2 foot deep in parts of the park. Again, that's why parks are really good in areas next to lakes that are low. But yeah, so it's one of those things, it's a tool to be able to use to understand how a system might respond to a rainfall event.
Good.
And one thing I would just add, in the hydraulic report, Shelley did a table of what those elevations are, the maximum elevations in the 1% storm, which will give us a bit of a preview of what the FEMA levels are likely to be, or likely to be close to those. So
So just to
Draft. Yeah.
rephrase that, 1% is the 100-year
right.
100-year rain event. So when you hear people talking about technical talk, 1%, that's a 100-year flood event.
Yeah. We don't like to use the term 100-year event anymore because people assume if you've had that amount of rain, you're not going to see it for another 99 years. That's not how the case. It's you have a 1% chance of it happening in any given year. So you could get it multiple times in a short period of time, kind of like rolling a dice and getting a 1 each time. That's what happens when I play a board game. I always get the 1. But it's the same idea, right? And so, but that's the colloquial 100 year is what people know it as. That's still kind of what FEMA historic reports say, although so when you see 1%, that's really what it is, because it's a better way to explain that risk.
Why don't
Okay.
why don't we move on to the culvert analysis?
So the main part of the study where the bulk of the cost was actually just coming up with existing conditions, because you have to get all your data. So the survey data, putting together all the models, Catherine's model, my model, to get this, and then the calibration of her model, my model, to get this existing conditions. But then the fun part comes into playing with it. And like what if scenarios, like it starts to give you an idea of what might happen if you model stuff. So one of the things that Mark wanted to know was Bridge Street up between St. Clair and Ellsworth Lake. There's a culvert there that's smaller and it appears to back up the water for those upper lakes. And what happens if that would be modified? But you know, if it needs to be replaced in the future, or if you were to just, you know, make a change on what that bridge looks like. So we did this was not engineered and designed, right? Like if you would do that, you need a structural engineer to tell you the size culvert I did was right, or it might actually, you know, all that good stuff. But we just threw in what's the width of the channel and how wide could I make a bridge opening and how would that impact the system? So we ran that scenario, and let's see. So I can look at it this way for both this was alternative 1. This one is the one I want. Yes.
Yeah, just
So this is St. Clair Lake, this is Ellsworth, and this is the Bridge Street
Right.
here.
Set the context. That's what you're looking up.
Right.
Upper chain for those of you in the lower chain.
Yep.
This is the city of Ellsworth. with Ellsworth and St. Clair, and then 6 Mile is off here. Screen right.
So to start with, let's look at existing conditions. And so this would be the max flood extent this was we called the calibration run. So this was looking from April to June of 2020, because we had some good data on all the lakes. Your chain of lakes, citizen science, we called it. People collected water surface elevations along the lakes would allow us to calibrate the model. So between that time period that we ran, this was the highest water surface elevations. And you compare that to the alternative one, and I have a slightly cooler looking way to look at this later. But, and I don't know if it showed up super well there. You could see from the existing conditions, the marshy, areas here, the elevations of the lake for existing conditions with the smaller culvert is higher. But if you do the alternative run with that larger size bridge crossing and you take off the calibration, the upper lake is actually reduced a bit, like the flood extents. And you can see this when I look at the profile view also. This looks messy. I'll get this cleaned up. So here, this is what we call a profile plot. This is if you were to cut the stream down the center, like as you wind down the river and you have a line, what would it look like? So this right here on the rightmost line would be 6 Mile Lake, and then this area here would be Lake St. Clair, the St. Clair Lake. Sorry, we have a Lake St. Clair like right next to my house. So I get the lake and the Clair switched. St. Clair Lake. And then this is that bridge that we're talking about. And this would be Ellsworth. So as we look at this, let's see, which one was this? This is the 1%. We want to look at something else. Plan view, sorry, let me switch. I'm going to go to calibration run and my alternative. So the existing would be this red line here. So anything kind of filled in with blue, just by changing the size of the culvert at the bridge street, you could see with the alternative, it lowers the upstream water surface elevation of those lakes quite a bit. That's how much that bridge backs up the water for those upper 2 lakes.
So just to clarify, the water will lower down to that red line, and then below the new culvert or the expanded culvert, the water will increase to the red line.
Yep.
So there's going to be some displacement of water level there.
Correct.
But it's not necessarily enough to cause any serious flooding downstream.
Right. And that's where before you would actually design this project, you would really want to make sure you have no, negative impacts upstream or downstream. And if you find positive impacts, then that's when you have a great project coming through.
Okay,
But you allow extra water through the bridge so you don't have the backup upstream, and it lowers it. But because you're allowing that extra water through faster, you have a rise in water levels downstream of it then.
and this structure that you modeled, the replacement for the culverts, what would you describe that as?
So I describe it as a box culvert. This is an example of the bridge. The scale of these plots are horrible, by the way.
That's the existing?
This is the existing, and on the vertical, it's 2 foot wide, and you can see down here, they're 20 foot. So this small little segment. So this looks crazy. But this is the existing, and it's a 8.2 foot rise in a 13 foot span. So it's a large culvert still, but I just threw one in I called it a box culvert. You could call it an open span bridge. And what happens if you had an 8 foot rise? So I kept about the same rise, but I widened it to 24 foot. And I arbitrarily chose that because it's about the full width of the channel. So you can see how changing it, from basically 13.1 foot to 24 foot, made a huge difference in what those water levels are. But without the model, you'd be guessing, well, what impact would this bridge have? So when you have the model, you can run those scenarios. Now, maybe this isn't optimized. Maybe this costs too much for this bridge and you don't need that big of a difference. Now that the community has this model, other sizes could be run. And it's easy to make that change in this one bridge to see how those things make an impact.
Okay. When you ran the 10% flood, the
Mhm.
100-year flood with the expanded size culvert there, the box culvert at Ellsworth,
Yep.
did the flooding, was the flooding worse downstream because of that culvert being larger?
So not really, no, because the larger the flood wave, the more that bridge still has an impact. Whether it was a small opening, it has a large impact. But if you have a massive, flood wave of that 1% flood event coming through, even though it's a larger size, it still has an impact. So while there is an impact, you can see that for the upstream, the alternative now is still a little bit lower, but it's not the same amount. Before it was like 0.8 of a foot, and here it was 1/10 of a foot. So it's a lot less impact. And downstream here, you can see that it's actually, very minor what those impacts are. It's a little tiny bit. I'd have to measure it.
So then what you're saying is somebody living on Intermediate Lake wouldn't have to worry that if they expanded the culvert there at Ellsworth, that they're suddenly going to end up having worse floods.
Correct. So like here, I just measured the delta Y. So the vertical difference was 0.018, so 0.02 of a foot.
Okay.
So I mean, that's extremely, yeah,
Okay.
yeah,
All right.
quite less.
All right. Thank you.
And so that's
So-
where knowing how the system reacts is important, because you have impacts upstream and downstream, but knowing, is it a big impact or a little impact, or, is it negligible? Where does those water levels, come in on the banks? Yeah,
Okay.
you can start to make plans on what you might want to do in the system.
Okay. So going on to the next issue, we've had a lot of discussions about the idea of dredging Intermediate River in order to have a faster reaction of the water level at the dam when I operate the dam.
Yep.
And we also talked a bit about how the Rapid River coming into the Torch River has deposited a lot of sediment there, and appears it's certainly affecting navigation and may even be holding up some of the water flowing down Torch River. So what were your conclusions when you modeled a couple of dredging scenarios for us?
Yeah. So I will say that, let me see. I can either show you from here or from the report. It doesn't necessarily matter. But for the dredge scenarios, again, this was just me and my cube 200 miles away. So if this was a real project, you would want to make sure, you kind of look at really what the slope of your channel should be. But I just made an assumption, like this shows, again, that profile along the river, what the high areas would be. And these are each cross-section elevation points, the lowest part of the cross-section. You can see some have, deposits, we'll say, that are higher. So then we just go in and like remove those, excavate, dredge them, what would happen? And I did not put in any fill. Like I'm not like increasing the ones that are lower, higher. I just said, let's cut the top off of any parts that we're doing it for this scenario. And that being said, it makes, it depends on where you're at. So the first one that we kind of looked at here was, let's see, sorry, let me see. Oh, this is the existing. Let me go to the proposed. I can pull it up in the actual model too, but sometimes this is an easier way to show actual elevations real quick. So alternative 2 was the Torch River dredge conditions. So that was modeling, doing some of that dredging just near Torch. And you can kind of see here my existing versus proposed channel geometry. So you can see these higher elevations were excavated down in the channel, and the water levels had a bit of an impact with that for this is for, sorry. Yeah, so this is the Torch River, and for the existing and dredge conditions for both the 2020 and the 1% flood event. So I don't know if you can see when I zoom in on here, it's not the difference between these two lines. It's that there's, and this is a little blurry, so maybe I need the other one. There's two lines right here and two lines right there, and that's how close they are. So dredging that much on the Torch really had no difference in water levels for either the lower flow events or the 1%. So because we had seen with the bridge replacement, there was a big difference between how, changing that culvert impacted both lower flow versus higher. You can see here the dredging on the Torch there where I tested it really didn't have an impact on water levels either way.
Okay, then we could conclude that if we dredged the Torch for the purpose of navigating
Yeah,
and giving boaters a little more depth, we wouldn't be tinkering with the water levels overall, causing additional problems somehow.
correct.
Okay.
Yep.
All right.
And so I created in the report a table here for that alternative run for each of the lakes. What my calibration run is my existing conditions for April 2020 versus the Torch dredge alternative for 2020. And then for the 1%, what the existing is versus the alternative for that. And you can see like they're the same numbers pretty much. Like here on Ellsworth, it was 1/100th of a foot different only on the 1% flood event. Again, extremely negligible. Intermediate Lake, it's showing the same exact elevations, same with Hanley. Looks like there might be up to 0.03 of a foot on Clam Lake difference. So very negligible impacts to the water levels in the system by that particular alternative.
Okay.
The other alternative was intermediate river dredge condition. And that was trying to figure out where on the intermediate river we would want to possibly excavate to look at that. So on that one, again, looking at the existing and the proposed, if you will, the dredged conditions for both the 2020 and 1%, we have this. And so I can pull this up a little bit cleaner elsewhere if needed, but for just, let's say the normal flow conditions of 2020, you can see that there was a difference with the dredging here on intermediate, and the dredging that I did was the straight line. So I just took the low elevation that we know is pretty much in the impoundment. And if we remove the sediment buildup that's in part of the impoundment there and kind of cut straight through until we get to intermediate lake, what would happen? And you can see that for the alternative for the lower flows, like the 2020 flows, water surface elevations decreased, as you would kind of expect, because you kind of have easier flow through that area. It's not backing up. But downstream, because the control point is the dam, the Bel Air Dam, you're not really seeing any impacts downstream. So you would, be able to, you would end up lowering water levels for like normal lower, like throughout the year conditions. But for the flood events, that's this higher one here for both existing and proposed, we're really not seeing any difference with the dredge condition. It's just so much water coming through. It's all about the dam and how that's, handling the water source elevation. So again, we
Okay.
have a table here that would actually show the elevations at each lake for that. So again, intermediate is where we are dredging, and you can see that for the, April to June 2020, it changes from 0.63 to 0.57. I mean, a bit, not crazy, but like the impoundment, intermediate lake changed from
It's velocity, right?
I'm sorry. Yeah, that's my problem. I was looking at velocities. The middle table is my water surface elevations. Thank you. It's been a long day. We left at 6 a.m. to drive up. So looking at Hanley Lake, you can see that it dropped it from 610.85 elevation to 610.79. Again, not a lot, but 0.06 of a foot. Less than an inch. And then at the impoundment is where it changed from, let's see, that one is almost no change, 607.03 to 607.04. And the 1% flood event didn't change too much either. So like you can just start to see through what's the existing versus proposed at each of the lakes for that. And it wasn't, I'm a visual person, So I like this one because you can see that the 1%, that 100-year is almost no change. And you can see some difference during the intermediate river, but
So just to conclude then that dredging the intermediate river would likely make it easier to control intermediate lake during normal periods because I'd have more flow at the dam and I could probably bring the lake down a little faster when I needed to, so on. But in the case of a serious flood, dredging the intermediate river is not going to make much of a difference at all what the flood levels are going to end up being on, say, intermediate lake.
correct.
Okay,
Yep.
thanks.
Getting pretty close.
I think we're ready for questions.
All right, so again, we're gonna transition to a Q&A time here. So first we'll answer some questions from the room, and then there's a whole mess of questions showing up on the web from those of you listening on Zoom, and we will get to those as well. So with that, let me repeat the questions as they're asked. So any questions here from the room? Richmond, go ahead.
When you're dredging, are you considering the removal of sediment or removal of sediment and the fact that this water is completely filled with growth that prevents flow?
So the question is, how are you modeling the dredge events? Are you just removing the fill or are you removing all the growth as well?
So in my scenarios, I kept the roughness factors, I'll say that vegetative growth the same, and I just, because it grows back so fast, and I just removed the actual sediments. But that's something you could look at, right? Like if you want to see what happens if you just clear out some of the vegetation, you could run that as an alternative run. There's so many ways you could do things that's where, for this was just to show some examples. And if you're to actually have a project where you're considering it, you would want to run those different types of scenarios. Quite frankly, for the dredge alternative, you'd probably want a geotech to make sure a geotechnical engineer looks at soils and sediments to make sure you don't have any issues. You don't want to create scour holes either, let's say. So you would have others take a look at it, but you can run all those different type of scenarios and designs based on, are you changing the vegetation? Are you just changing the cut?
The vegetation there.
Yeah.
I think you can hardly paddle through it. And
Right.
I'm sure that it inhibits flow.
Yeah.
Mhm.
Okay. Other questions?
How close was the August 10th, 2021 storm to a 1% storm?
So the question is, how close is the August 20th, 2021 storm to a 1% storm?
Yeah.
That's the storm that-
Right, August 11th.
5 inches
Yeah.
last night.
But that was in one specific area. So it's important to
So it
understand.
didn't do the whole chain, you're saying?
Yeah, so, when the Army Corps of Engineers talk about a rain event, they're talking 5 inches over the entire watershed, as opposed to, we know, because of some of the rain gauge data we had, plus the radar data shows it, that there was not, a really heavy rainfall kind of in the Cedar River, kind of in the Grass River area, right?
Mhm.
Yeah. it was
And
mainly
it
in-
really hit that area really hard where the Grass River natural area is. And you saw the bridge on Comfort Road go out. And some of the other areas farther north and farther south didn't see as much. So you need to take that into a context. Sometimes you can say, we had a 5% or 5-inch rainfall there. Some of us can remember times when we got more than that, but you got to kind of spread it out over the entire area and say this entire area gets 5 inches. And so that's a little bit of a difference.
And I would say now with the model that we have, you can get that radar data from that storm event, run it through the model and see, it's another way to now continue to like calibrate your model with more storm events and more observed data. So that's also like where I would foresee taking that HMS model is now you can continue to make it better by just running additional storm events.
Yeah, we could run a case where we dump a lot of rain
Yeah,
in that area,
Yep.
but not up as much as at
Exactly.
Ellsworth or down at down in Skickalog and Elk.
If you
Yeah,
want
so
to
those
just
cases,
run, like the pop-up thunderstorms, when you get the radar where you just get the cells moving through, you can run
Yeah.
that now.
those
through
are
HMS.
things that we could do.
Yeah, you could run the actual volume of rain that happened for that particular storm event in.
Yep.
Yeah, good. Pete?
Yeah, no question about it. The Finch Creek watershed had a 1% event that night because Elk Lake went up at least 8 inches. And that's a lot of water. Yeah. From what I could track, I checked all the gauges that I have available to me. And that was another one of these cigar shaped formations from the coast on the bay going northeast and cutting right across. And it was dead on the Finch Creek watershed and the Rapid River watershed, the lower Rapid. So
Good.
Yeah.
Back here?
Just wondering, you have an area that has really good topsoil, you're gonna have a lot less water end up in the lake. You have an area that's right on top of gravel or sand, I'm guessing that the lake that's there is gonna fill up a lot quicker. Was there any correlations done along that? See my train of thought.
So the question for those of you on the web is all about the water holding capacity of soil and how that's modeled in the model, which is a key component. Some soil will hold water more. Some soil can let the water just pass through. So
Yeah, so when I was talking about generating the inputs for the subbasins, what we look at is it's called the loss rate. Like when it rains, how much water basically infiltrates into the soil. And the way we calculate that is based on the soil type, the USDA soil information, is it sand, is it clay? I have to look at it more at a more general level at that level. And so it's a bit more generalized than, field versus field, because I can't get really down to that level at this size of project. But that's what's taken into account is the rain falling on a big area that's been like paved? Is it falling on a farm field? Is it falling on an area there's gravel? There's the water's obviously going to infiltrate down. And all of that is like part of how when the water falls on the subbasin, how much water of that rainfall is actually going to be just trickling down either and then flowing, like sideways through the ground to the stream, how much is going to flow down into like the aquifer, and how much is really going to flow into like the super deep aquifers where it's unlikely to actually make it out to the surface lakes anytime soon. So that is all part of what we try to capture in the model. And that's actually a very important part. Soils is one of the most important part of doing this type of modeling, that the soils and the slope are two key components.
good question. Hold on. I think there was one over here. So question is all about the calibration of the model and fitting it to real world data. How often would you think that we would have to recalibrate the model going forward?
I'll let you start with the hydrologic one.
Okay,
but-
so I'm gonna say after every rain event and every piece of information that you have that's new, I realize that's not always, it's really going to depend on how much money you have to devote to this and how much time you have to devote to this. But I would say if you have someone to like look at it after every large rainfall event and say, hey, if you after the storm, if you can download the radar, run it through, hey, how close were we to, the what we saw, like the observed water levels, like how close were we, it's calibration. As I joke with some of the newer engineers, I'm like, I can calibrate this model until I retire. But, at some point you kind of have to just stop, and that's the best you can do. But, you guys are all here. You're collecting data. You're seeing what's happening. So you could theoretically, after a large storm event, download the data, run the model, see what you got, see if, what your starting conditions were. Maybe if you run enough storm events, you can get a better handle on, hey, it didn't rain for 5 days. So we should start the model with, we assume that there's like not a lot of water in the ground. And we ran a storm event, and you can kind of start developing a relationship and a feel for how your system responds. So I wouldn't say it's a hard and fast type of thing as to how often to calibrate, but I would say if you can calibrate with a couple more storm events each year, you will start to build, a feel for how everything responds.
I want to make sure that the folks that are watching this at home understand when you talk about calibrating and also about the citizen science program. Okay, there's a bunch of the volunteers are in the room with us here. What this involves specifically is people at home who were checking their rain gauges after every rain event and then reporting the information that they were gathering at home. These are all volunteers that live in the lake basin, and that the county had purchased about a dozen lake level gauges, which we distributed through all the lakes, so that we have actually been tracking the exact levels of all of these lakes now for this will be the 3rd year, and also have been tracking the rain gauges. So the reason that we can continue to calibrate is because we have volunteers that are willing to do this for us. And I just want to make sure that it's clear to everybody that this is not some magic data that just gets delivered. It's people out there actually observing the phenomenon and tracking it. And I want to reiterate, the county thanks profusely all of the folks that have been involved in this project. And now you see how important the work was that you were doing at your homes, especially Fred Siddle, who did a masterful job of coordinating the entire project.
Indeed. Good. You had a follow-up question. So the question is, how did we incorporate the operation of the dams? And actually, the Bel Air Dam and the dam at Craven Pond are built into the model. The dam at Ellsworth at Elk Rapids is not part yet. That's a future study. But within that, let me turn it over to our experts.
Yeah, so a lot of times if we model the operation of the gates on a dam, it's because we have an operations manual that we can like code in. If the water levels get so high, this is like the automatic response of the operation. Bel Air doesn't have that. You have Mark's expertise and years of experience that run it. So for us to calibrate it though, it was easiest. The reason why we kind of chose that April through June timeframe for the calibration is because the gates were fully open. So it's easy to say we have like a 3-month stretch where gates were fully open and we can just run the model, and we have all of that, great citizen science data that we can, model and calibrate to that. So another part of your calibration would be like, I was in literally a room of maybe 35 hydraulic engineers last week at we called it our community of practice meeting in division. And there is a joke that hydraulic engineers will keep working on a project until funds run out, or it's like someone takes it away from them. And that's 100% true.
That's
because
100% true.
usually Garrett's the one that says money's up, your project's done. But that's would be, I think, a great future project would be if you have a, a good set of time where, you have the gate at a half a foot, you have a gate at, one gate fully open only, you have, 2 gates half open. You have the existing conditions, you can model it, and you can, with the observed data, and you can see how that runs and calibrates. I think that would be great. But our models were run with just gates fully open because we had a good chunk of time with our calibration data, and for flood events, gates are usually always open. So if we wanted to get an assessment of how the system works in flood events, it runs fully open.
Okay, so at this point in time, there are some really good questions out there on the web, and I want to get to some of them. But as the people here in the room have further questions, I'll try and get to them. So first of all, a question here. If you were to put error bars on projections of the model, what would they be? Plus or minus 5%, plus or minus 10%? That gets into the accuracy of it.
Yeah.
I really don't have a good answer for that.
You can say that your model calibrated very well, though.
I mean, and based on, the way that HMS models are reviewed and the results that are typically looked at, it does meet the pretty good calibration. There's some guidance as to how to determine, what is good calibration versus very good versus, and I can't remember if that was the exact terminology. But in overall, it calibrated pretty well based on the guidance that HEC is able to develop. Hydrologic models, it's a tough thing to get right, to be honest. It's very hard to measure accurate rainfall across the whole watershed. It's tough. You don't know what's going on below the soil surface. So it's a difficult thing to work on to try to get, your groundwater correct and, the water flowing overland. So we do the best we can, and we keep at it until we can get something, that we think is reasonable, that meets, as well as we can in terms of observed data. And I really don't have a number for you, but I feel it did calibrate pretty well, and it did meet some of the HEC published guidance for how to qualitatively determine how well the calibration turned out.
Okay. Another question from the web. And Mark, you might want to talk about this. What's the long-term plan for use of the study in the county? I mean, you and I could probably talk to that a little bit, but.
Well, I think that's largely to be determined. I hope it's going to be a point of discussion among the Board of Commissioners. And, but I do think that now that the study is complete and it's in the hands of our community and it's public domain, there are no restraints to taking this study and running. And I would personally urge, especially the riparian community, that you have an opportunity now to take control of your fate in a way that maybe you never had before, and to step up and take this thing to the next level. The riparian community in Antrim County has got the wherewithal. It's been proven by the volunteers that we collected on the lake level committee that worked so hard on this, that there's a lot of wise people and talented people. And really, I think it's a clarion call. It'll be a test to see what we do. I don't want to see anybody sit back and expect government to solve this problem. I think everybody needs to understand that this was never part of my job description. And there will never be a county hydrologist in Antrim County. This is something that we had an opportunity. We seized the opportunity and we made it happen. And it's a wonderful thing, but now it's up to the community to step forward and decide what it wants to do with it. And I urge my neighbors and friends to do so.
Okay. This gets back to our last question. Is the Elk Rapids Dam part of the model? Can it model what would occur if the dam failed, like what happened in mid-Michigan? So I think we already talked about that, talked about part one. So no, the Elk Rapids Dam is not part of the model. Yes, we did get some survey data around that area, so it could be added. So with that, again, make sure the experts have a chance to say.
Yeah, so when we scoped it out, we were really kind of wanting to know how the lakes all respond to each other. And that was kind of the focus of our project. So since there's pool elevations that are kind of known for the dam, and then you have to get into the operation of how they run it. And that's a little bit more, difficult and time consuming. We kind of left that out of our scope of work because we want to kind of get the most bang for the buck, what we can for learning about this lake. So that can be added in. I would say, the Bel Air Dam is in there. Can it be used for, things like dam breach modeling? Yes, that's a question Mark had asked us. And the thing there is it's expensive to run those models and that study because there's a lot that goes into it that people don't necessarily recognize or realize. Usually when you do some kind of like a risk assessment on a dam, you have a team of engineers that kind of review the as-built data. You go out and study it. You'd have a structural engineer to look at the actual, concrete structure. What's the condition of the gates? What's the condition of the miter blocks? What's the condition of the structure? Geotechs to look at the impoundment itself, the earthen part of it. You have hydraulic engineers and you kind of have to do an assessment. So risk is pretty much, what's the probability of failure and then the consequences of the failure. So you would have to have all those engineers come up with, you kind of brainstorm failure modes and you'd come up with what's the most likely ones that would happen. And you have to give a probability to it. And then you can run those dam breaches or those failure modes in your hydraulic model. And the model will do that. You can do dam breach scenarios. And then you get the consequences. And so, but the risk of it is what's the probability with that? The Corps has an entire specialized team that does it. We have a risk management center that's run out of different areas. I kind of did 50% of my time for a couple of years working on it, which is why I know it, because otherwise our district doesn't do it. But like when you get into those failure modes, is it that a gate fails? Is it that a piping failure, we call it, in the earthen embankment, right? Was there maybe an animal burrow that like made a little hole and now water can seep through it? And would that part fail? There's a lot that goes into that type of study. So can the model do it? Yes, but that's not a quick run. Like changing out a bridge is a very quick model run that someone could locally do easily. Doing some kind of
An official dam failure study is pretty involved.
it's pretty involved. Yeah.
And the short answer would be that I would like to add Elk Lake and Elk Rapids Hydro Dam as soon as possible to the model so that we are modeling all the way to the bay.
Mhm.
And and my next priority is to do exactly that, a dam breach assessment, both for the hydro and for the Bel Air Dam.
Okay, good.
So,
Good.
well, that would involve Bel Air, the village of Bel Air, to talk to us about it, because that is critical structure. If that one was to fail, it would be a extraordinary situation at the Bel Air Dam right downstream. So all these things are linked, and I'm hoping that the release of the model is going to make that clear to people, that all these things are related. It doesn't matter if you live on Elk Lake, what happens up in 6 Mile Lake affects you. And we all need to just start thinking in those terms. So.
Okay, moving on. This is another overarching question. Now that we have the data, and I think Mark just spoke to it, which is why I'll bring it. Now that we have the data, what are the next steps, action items for this watershed? So I think Mark just spoke to some of that. You know, we intend to continue using this model, continue developing the model. As Mark said, we're going to hopefully be able to add the Elk Rapids Dam and the stream out to the bay into the model. We have more scenarios that we want to look at, but all of that depends on further use of the model, further development of the model, and a lot of that's going to be done by volunteers within the riparian community. So there's more that we want to do, but some of that will have to be determined on what capability and what resources we have. Good question. So the question from the floor was, if we get this model, is somebody going to be able to use it? Well, we assumed you would for us. No. So we actually.
That's exactly what we need to discuss.
Yeah.
And I made sure that a number of people in private practice and so on were at the meeting earlier for the technical handoff. And Dave Christian has written up a letter for a request for proposals that we are going to distribute to all of the higher education institutions in the state of Michigan, the hydrology departments and so on, and not stopping at the state line. The HEC-RAS and HEC-HMS modeling system is now at the core of every hydrology curriculum in the nation. Anyone who is working in advanced level about water, not just about the engineering aspect of it, but also about things like nutrient transport between bodies of water. You know, hydrology is at the essence of how a plant works, an individual plant, and it's also at the essence of how a whole ecosystem works. So here we are with this great gift, because we have got a really comprehensive model started now of an important chain of lakes in the state of Michigan, which is representative of many other lake chains, say, you know, Mullet Lake and the Inland Waterway and those types of places. This could be a wonderful resource for a research department, for somebody working on a PhD, to step in and maybe improve the model in some way as their dissertation. And so what we want to do is warmly encourage and welcome people like that and come into the community. And hopefully we can leverage some of that effort for our own purposes, for what the local community's objectives are. But, you know, we had to have the meeting. We had to throw this idea, show people what we've got. And now the conversation begins exactly what you're asking, Dawn. That's what exactly the kind of discussions that I hope we have about where do we go now. So.
Yep, good. All right. So question from the web here. Are there plans to establish USGS gauging stations in the system to help validate the model? I assume the field observations provided for river stage collected by the public, etc., are at surveyed sections cut at riffles, i.e. hydraulic sections. Last, do you have confidence that the model output predictions through time could contribute to a regional curve for ungauged streams in this hydrophis region, or will it just reflect a localized curve for this system only? After the clarification offered over the model reports, I assume these questions will be answered there. So that's a big,
We can break it into little chunks.
yeah.
As for the USGS, well, first of all, for the citizen science data that was collected by the volunteers, those are on the lakes. So that's not on the rivers themselves. It's not at riffles. So when he talks about riffles, and there's riffles and pools a lot of times, and that riffles would be considered a control point. It's where it's a little bit higher elevation, and the channel naturally get high areas, low areas, especially around turns. And so that's where a lot of times USGS might want some kind of a gauge. So there's no USGS riverine gauges in the system at all. There's one USGS gauge on Intermediate Lake, I believe. And so that's why the citizen science data was so valuable. But those are lake ones. So, which is great. As there are plans to establish USGS gauging stations, I'll leave that to Mark, but I will say this, USGS gauging stations are expensive. And other projects where we've had to have them put in for a very specific purpose, it can be 40,000 to install the first couple of years because they have to have the manpower to go out, and then they have to survey it multiple times to get a rating curve for that location. And then there's a yearly maintenance cost. So the USGS has limited funds, as a lot of places do. So they tend to not put in any new ones unless there's a very specific need or reason.
Right.
Maybe you could argue there's a need because of the dam and have those conversations with USGS, but sometimes getting new gauges put in is extremely difficult.
Yeah, we're spending on the order of, the county pays for the USGS gauge on Intermediate Lake. We spend about $600 to $6,500 a year just to host it. And that was already installed for another purpose originally. So on the other hand, the citizen science effort, I think we spent a little over $1,000 for a dozen lake level remote gauges. And because of Fred's expertise, we're very confident in the accuracy of the data that we acquired.
Yeah, I would say early on when it was getting described to us, they're like, would this be helpful? And they're all localized like to a local datum. We're like, that's helpful to understand the response of the system, but unless we have actual elevations and them surveyed in, that's not as helpful. So right away, you guys had them all surveyed in. So we had actual elevations on all of the lakes there.
Yeah.
So
And I just gotta, I gotta plug people for what they do. The Three Lake Association was instrumental in buying equipment for survey equipment and stuff to help us with that. The Intermediate Lake Associations, supplied the volunteers that form the core of the lake level committee. And then, we've got people, members of the 6 Mile Lake Association measuring up in 6 Mile. It was truly a collaborative effort. And I hope that we can continue that kind of a network going forward so that we constantly have data in order to calibrate the model.
yeah, the more years of data, the better.
Right.
I mean, we get excited when we have data because sometimes we don't.
Yeah,
And
so the primary tool that we're using to calibrate the model is the lake level data that we have. And
Yes.
so, I mean, that going forward, that's our plan, to continue to use that. All right. Here's another question specifically about Intermediate Lake and the dam. I believe there's about a 16-foot drop from the current spillway at the Bel Air Dam to the river below. So there's a lot of potential for gravity to move more water. Since we often have difficulty meeting the court mandated water levels for Intermediate Lake, will the model demonstrate what a modification to the Bel Air Dam, i.e. lowering the spillways, will produce in moving more water so that we can better comply with the mandated water levels and reduce flooding? I believe there is about a 16-foot drop from the current spillway to the river below. So there's a lot of potential for gravity to move more water. So, what I guess the gist of the question is, could we modify the gates to have a deeper gate and better, what would be could you model that? And if you modeled it, would that have a chance at better controlling lake levels on Intermediate Lake?
the modeling part would actually be pretty easy. Yeah, we put in sill elevations of the gate. So we put in the actual elevations of the gate, the size of the gates, that information. So you could tell the model just to move that sill elevation lower or change and then change the height of the gate even. So you could model it to see what the results would be. That being said,
you would have to do a little bit of work with the HMS as well,
Yes.
because the HMS model is predicated on a curve of how the water flows through the dam. So it wouldn't just be the HECRAS. There would be a little bit of work between the two, but it can be done.
And that's the big thing with this system is there's a lot of iteration between Catherine's HMS model and mine, because if you change one thing, you kind of have to change it in sometimes in both to get my inputs, correct. So the modeling can be done between the two. The bigger thing would be the cost of renovating a dam and ripping out
Yeah, I
concrete
mean,
and
conceptually, we can look at it, whether or not structurally
the dam could
that's
handle it.
actually a design that could even be feasible. I mean, that's a whole nother issue.
That's a whole nother issue.
Yeah.
Yeah.
So,
Okay, so there are a couple questions. One question I want to get to again from the web that kind of I think you gals can respond to that really we haven't touched on as much. Can we use this model to determine where changes can be made to improve the flow through the whole water network? Then when there are high rain events, there may be a more gradual increase and decrease of water levels. So that, the question is, to me, and I know we spoke to some of this, when you have a high water event, like 100-year rain event and you get 5 inches of rain or, whatever, could we just modify some of the waterways, to better handle that?
in general, yes, you can use the model to try out things like that. What specifically you might want to do, I'm not 100% sure. I'm honestly thinking, things like, well, I mean, you've already got huge lakes in the system, and usually I'm looking at like building retention ponds, which are, like an acre. So, yes, I mean, you can try to see if there's any way to, because right now, just throwing out some ideas, just conceptual. All of the outflows from the lakes are unregulated. There's no structure like controlling the flow out of anything really, other than, maybe like a culvert that has a little bit of control over St. Clair Lake. So, timed out. You could use the model to try to see if we stored the water differently, or if we, changed how the water flows out of one of the lakes. That is definitely something that could be run in the model relatively easy.
I will say this though, it
But
becomes
it's also-
complicated because
Then
if you slow
yeah.
water down in one area and then speed it up in another, how it's going to work on the system as a whole. You change one thing here, it can impact throughout the system. So
Yeah.
it's yes, it could be done, and that would be maybe a great thesis project for someone who has
Yeah.
plenty of time to run a lot of models
Yeah.
and kind of see if they can optimize something. But also we like to keep things natural as much as possible. So then it's, what might be feasible. But yeah, the models can definitely be used as a tool to do something like that. But also if you change routing, again, you might have to change it in both the HMS model and the HECRAS model to kind of do that.
To get the full idea of the impacts, you would need to run both.
Mhm.
But I guess I would also refer to what you were speaking to earlier, that when you get these flood events, during normal operation, water is within the banks.
Mhm.
And that pertains to one flow regime and one hydraulic analysis. But when you get a 5-inch rain, very quickly the water flows out of the banks, and that's a different flow regime, correct? I mean, that's a different horse to handle. Okay, we're almost done with questions here. And one more from the floor, Janet.
We have been truthful here that now this should better than anybody else based on the work you've done model together. If you had time to go test something, what are the top 3 things that you would go test the model
So for the people on the,
have an impact on the lakes?
So question from the floor here was, what are the top 3 things that you would, if you had the time, attack on this model to make to improve the model or improve the lake, the chain of lakes?
You can start.
So I actually did include about 6 different things that I suggested that could be done to improve the model. One of the things that we suggested is, collecting updated bathymetry for the lakes. The information we have for, the lake below water lake information is very old, and we had to make some best engineering judgment as to how to incorporate that into the LiDAR data. So I definitely would recommend collecting updated bathymetry. It's a pretty costly effort, we understand. So I would recommend, starting with like some of the shallower lakes, because it all depends on like a curve. And if you have, if your storage is off even a little bit, it can have more of an impact on, how much storage you have and how much flow goes out and things like that.
And those shallow lakes are the
And-
ones that might have sediment.
Yeah,
built up
and
since
also-
the 50s, which is
Yeah.
when the last known
Yeah.
depths were mapped.
Yeah, that's also another thing, is you might have sediment there. And then I suggested, I had to make some assumptions in terms of like how water flows out of the lakes. So if anyone is interested in, I had suggested developing, an informational rate, like called a rating curve, like, as the water comes up in the channel just outside of the lake, how much flow do you have? So you have an idea of when the water comes up, how much flow is coming out of the lake. I had to make some assumptions and use some information from the hydraulic model. So there was like a back and forth. And so any information to more accurately gauge how water flows out of these lakes would be helpful. And especially if you start doing like a range of gate configurations at Bel Air Dam, you can kind of get a correlation between, hey, if there's this many gates and, the water's flowing out of the lake, and how does that impact things? And then also, so the same thing down at the lower lakes, all the rating curves out of the lakes would be helpful. And then possibly installing even some relatively inexpensive discharge gauges at some of the major tributaries coming in, just to have a better way to calibrate for the tributaries, because again, we don't have any USGS gauges, and all of the water level gauges, while helpful, they were on the lakes. So I don't have a good way to calibrate, like the Rapid River or, all the smaller creeks coming in. So those are some suggestions that I had included. Also, some groundwater information, that would be great. If you ever have the funds, a groundwater modeling study, or it'd be again a great project for a PhD project, perhaps, is a groundwater modeling study to have an understanding of how groundwater interacts with the surface water here, because there's a pretty big component in terms of how groundwater affects the system. So those are all be helpful things for the HMS model.
I would say that we have, great information on the lakes now with the citizen science. Catherine mentioned the Rapid River. I know there's been, flooding on that river, and when we were looking at the output data from Catherine's model, but nothing to calibrate that sub-basin region. That's where we saw a lot of change from the estimated discharge from what the state puts out. So that's where if we saw the greatest, change, we think our model's good, but that's not an area we had calibration data, is that sub-basin tributary coming in. So again, either getting some discharge measurements on the Rapid River or getting a little bit more information on that, I think would help with knowing a little bit more, accuracy of that, because I think that was one of the biggest unknowns.
All right, very good. So
Real quick, I was going to chime in real quick. So I think where you're getting at, I'm sorry, what's your name again? Janet. Going forward, like if we were to make an engineering recommendation of structural improvements, both from a flood risk standpoint. So everything that was just mentioned here was really just further developing the data that we have, all driving that train going forward. Like this study was really, and the purpose of it on the FPMS non-structural, that's exactly what it funds. It funds basically the baseline, gives you the meat of what, unfortunately there's a cost constraint involved, but it really sets, like I said, sets the baseline to build off of. And we could run conceptual ideas and recommendations all day, every day. We could add dams, we could add flood walls, levees, stop log structures, gate structures along the entire system, wherever there's high risk. So it's really, my recommendation as the flood risk manager for the Army Corps here in the state, and for the FPMS as well. It's really a matter of the community has to come together and understand what their goal is, what the objective is, right? So you're gonna have to move, once we get all the data lined up and move forward, you're gonna have to do, feasibility studies. You're gonna have to involve economics, environmental, with snagging and clearing of the brush, contribute, we don't know. So, that's the scenario that had to be run, levies. So, benefit the cost, that's what we're talking. So the city comes together and says, what are we focused on? We focus more on recreation, or we focus more on, with fishing and kayaking and all that? Are we more focused on protecting these high risk, the 1% flood? Those are things that need to start being talked about and addressed. And then, this isn't the end all be all for the Army Corps at our district, right? We're not just like, here it is, good luck. Good luck to you, right? So right now, for this study, this purpose, the funding, is exhausted, but that doesn't mean there's been an influx of FRM funding across all government agencies the last couple of years. All right, it's been a top priority, included in infrastructure bill. It's been a top priority. The money's there. All right, the benefit, and this is the only project that I got several projects that I'm working on in similar nature, is that we have the backing, we have the leverage to go forward working as a team. And I don't know if you guys have heard of Silver Jackets team in the state of Michigan at all, but that's basically, I'm the coordinator of that from the federal side with the state Eagle. That's what we do. We meet bi-monthly. We talk about how to better improve situations just like this in this state, right? Obviously, we prioritize certain areas based on, situations there with certain communities, but and honestly, and I advocate a lot, and I do a lot of work to justify rural areas getting assistance in federal funding. They don't have the money to 50-50 cost share a $500,000 project, right? So that's my job, and I do, we work as a team, and we drive that train and say, hey, we need this assistance. So just want to let everybody get a little bit of the comfort zone here is we're not dropping the ball. There's still funding available, and then I will definitely work to assist going forward, if for Catherine and Shelley to be available, if Mark or your guys' team comes together and says, hey, we want to look at all these. All right, we ran the model, we see these high risk areas, FEMA confirmed it and said, now yes, you're in this floodplain, your insurance is now going to increase. So that's the case. And so what we want to look at, hey, how much rough order of magnitude could you give us structural measures, conceptual structural measures, if we had a flood wall here on this, in this area? Sure. What I mean? Those things don't take, I shouldn't say shouldn't take too long. The modeling takes obviously a long time. All right. So going forward, I know I probably just, I haven't talked this entire time. So,
I didn't want to
So-
put you on the spot.
No, I'm good, yeah.
I'm sure glad you put yourself
Yeah,
on
yeah.
the spot.
Yes, I'm the money guy. All right. So I'm the money guy, and I run the programs, and I like to see stuff start to finish and like to see improvements made. So, but we can't operate, whether it's state, federal, local, whatever the case may be. We can only operate as to what your needs are, right? You requested us to conduct this study to provide you with this with this current information and with some recommendations. Here you go. All right, now how do we move forward as a team and mitigate the issues that are having? But those have to be like thoroughly detailed and identified so we can get it done.
We'll start working on it.
Good. No, so it's a collaborative effort with the entire state. So with that Silver Jackets team, the state of Michigan, it's their program, but I'm heavily involved as the federal, like I'm the federal lead for it. So I work really close with FEMA, USGS, the state, even, universities, other non-government agencies. So what we do is we basically do a round robin of what we have going on and outreach efforts. So we've had, I think Mark, you've attended one of our HECRAS training for, I think we call it Indiana HECRAS, but there was others involved in that. So education outreach, I have a dam safety education outreach with Eagles dam safety team coming up in the next couple months. They're going to identify a few regions, and we're going to do some in-classroom training and out and do some, go over some operation and maintenance of, for private dam owners and stuff like that. So that'll be coming out from the state here pretty soon once we get a schedule dialed in. So yes, to answer your question, if you're going for federal assistance, from what the Army Corps see, every agency has different authorities, right? So FEMA has their grants, state has their grants, HUD has their grants. Right, so this is how this happened, right? So Mark found out about our FPMS program, which is 100% federally funded. Then that came through us, right? There's other grants. So if you want to move forward, let's say that you want to, you all decided, and through a feasibility report, everything backing your engineering analysis and everything, and you select an alternative that's best fit for your need, then you start looking at, okay, what if, if you can't fund, you can be able to fund a $200,000, $300,000, $500 million project for structural improvements, probably not, right? Unless some, like the Great Four Lakes Task Force that's supporting the Midland project, they raised over $1 million, so they were able to contribute funds. We did 50-50 MAC cost share for that study. But, you find out what authority, okay, what's available. And, a lot of it is a funding threshold. We have a lot of authorities at the Corps. We can support construction. We can help fund construction. We can 50-50 cost share, and a lot of it just depends on the justification of it, benefit the cost, right? I'm telling you right now, it's really hard to get those construction projects approved and paid for if it's not a lot of benefit. And what I mean by benefit is protecting life, property, health and safety. You know what I mean? If you're trying to say, just get it done in $1 million project that, just for water to flow better, that'll be a little bit tough sledding. So to answer your question, once again, it really depends on where this goes from here and where it ends up and what you've developed and what you have lined out. How do you want to proceed forward and what you want to achieve?
But it would just be for the Corps through you, like other federal agencies.
Yeah, I'm just right. It's just Corps, but you can actually, my contact information be put out there. You can definitely come. Anything flood related, anything flood risk management, flood related in the state of Michigan can come directly to me, and then I can.
Because you have contacts.
And contacts FEMA,
agencies.
right?
Yeah.
We're diligently trying to work on a one-stop shop hub database portal online for all of us agencies to combine and store all of our information. And that way you can go, just navigate to, what specific need that you have. We haven't had yet to get that. We've got it. It's been brought up. It's been brought to the table. We just haven't really figured out, and really it's who's going to maintain it, So like all the agencies, we're overbooked, overstaffed. We got all these projects and juggling, and it's really a matter of, that's kind of where the buck stop was like, well, who's going to maintain this thing? And we're like, oh, yeah, we got to figure out. And nobody jumped up and raised their hands. So it might be something even, I don't know. We have a lot of legalities, right? So unfortunately, that's just how the system is. It's how the government works. Is we do have a lot of restraints and to what we can and can't do. And so following that legal route, along with obtaining the funding, along with, a lot of other several things, it definitely takes a large effort but it's not entirely. What's that? For sure. Right.
Thanks, Gary.
Okay. So I think that covers almost all the questions that were asked. There were a bunch of people responding, that really appreciate the work that has been presented here and really impressed with the work. So again, we thank you for that. Last, and I, there are a couple questions here that remain, but I'm going to leave them for another day.
Yeah, we're over time now.
Yeah, we're over time. Do appreciate everybody here.
I have a comment.
Okay.
I think many people don't realize that when you raise the lake level by 4 feet, which they've done here, the groundwater level increased by 4 feet. And the groundwater levels don't go up 4 feet and then stop. Groundwater levels go up, and at the end, Manslota, there's no change. All the way down there is the change. There are many houses on Intermediate Lake, on 6 Mile Lake, that think they're flooded from high water levels. They're flooded because groundwater levels are up a long way. And the solution people have is to put pumps in their houses and pump groundwater out day and night.
That's right.
There are half a dozen houses, probably more than that, on Intermediate Lake that are pumping water all the time. The other problem is that when you have the water at the surface, as you do, you've got a drain field which isn't functioning properly. You've got a drain field of groundwater when they're mixing, so you have multiple problems from it.
All right. Thank you. That was Richmond Brown, by the way, giving those comments, who I believe at the age of 97. Some of us know him when he's riding his bike down in Central Lake Village, but I just on a personal note, Richmond is a retired hydrologist. He's the only living member that I know of who is actually named in the lake level circuit court ruling as an expert witness about the circumstances and in determining the lake level on Intermediate Lake. And I'm just so delighted to have you here as a guest, Richmond. I know you were probably doing your work with a pencil and a paper pad when you were doing your calculations, logarithmic scales and stuff, but it's so wonderful to have you here. It is. It's the greatest place in the world. Yeah.
My last place was Antrim, and we were there for 4 years. The end of 2 years, we came back here for our vacation.
Yeah. Well, thanks again. Good to see you.
All right.
Also, one last thing, Dave, that we've got to plug is that our next event that will be addressing a lot of these issues is going to be on July 12th. And it's being hosted by the Three Lake Association in Central Lake at Thurston Park. And there'll be a presentation there, and hopefully it'll be the next stage in this community discussion about where we go from here. So I strongly encourage everybody to look for the publications on that and to be there on July 12th.
All right. Thank you all. So with that, if you're on the web, this meeting's closed, and we thank you for attending. Really appreciate it. And thank you. Thank you all. We're done.